mention the direction of the oscillation of the electric field, of the vector electric field. So that's what I want to notice with you again. Yes, is what I want to remind you. And now we will continue with some cases. First, we're going to talk about the polarization by reflection. So showing you in this figure is an unpolarized light. So how can we recognize unpolarized light? So we see here the red vectors shows in which is the direction of the oscillation of the electric field. And inside this light, we see like the electric field distribute randomly. So in this case, we get the unpolarized light. Here you got the unpolarized light. And also, last time we discussed the linearly polarized, right? So if the electric field only oscillates in one direction, like last time we talked about the example of the Y component only along the Y axis, or along the Z axis, we have Y linearly polarized light or Z linearly polarized light. So in which the vector electric field only oscillate along one direction. So we have the linearly polarized as well. And we can have also circular or elliptical. We will discuss right after. So in this case, first, we consider here one example in which the unpolarized light incident. So here they also denote for the special case in which the angle of incidence is equal to some special angle. They called polarizing angle. But in general, it can be incident at arbitrary angle. However, I want to discuss with you right this example, because here you see also when the light impinges on this surface, so this surface is a so-called reflecting surface. Here the light is reflected, and also the surface is the interface between two different media with a refractive index NA and NB. So the light also is reflected, or we say the light is transmitted as well. Yes, transmitted. So sometimes you use the word transmitted. Transmit. When the light travels from one material to another one. So we have that here in this case. So we have also this kind of plane, which consists of the normal and the incident ray. It is called the plane of incidence. So it is some concept, and we will see the polarized light of the reflected rays and the refracted rays, how they behave. So for most angles of incidence, the waves with electric field, and also I denote with bold here, means vector electric field perpendicular to the plane of incidence. So I note here again, plane of incidence. So consists of so pay attention on that. You have some concepts related to the phenomenon. So the plane of perpendicular to the plane of incidence. So plane of incidence and the reflecting surface are perpendicular to each other. So perpendicular to the plane of incidence means that parallel to the reflecting surface are reflected more strongly than those for which vector electric field lies in the plane. So the case, the incident rays, which the polarization perpendicular to this plane of incidence, reflected more strongly than the other case. And so the reflected light is partially polarized in the direction perpendicular to the plane of incidence. Okay. However, it's some particular angle of incidence. They call that the polarizing angle, theta p. P denotes the polarizing here. So the light for which vector E lies in the plane of incidence is not reflected at all, but is completely reflected. So you see here, if the unpolarized light is incident at the polarizing angle, as shown in this figure. So in this case, the reflected light here is 100% polarized, perpendicular to the plane of incidence. So only the component which polarized perpendicular to the plane of incidence is reflected, right? And also at this angle, the light for which vector E perpendicular to the plane of incidence is partially reflected and partially refracted. And the reflected light is therefore completely polarized perpendicular to the plane of incidence. So we have in this case, and the reflected one, which is partially polarized parallel to this plane, so I mean the plane of incidence here, the reflected light is a mixture, so it contains both the parallel one to the plane of incidence, and then the other part is the perpendicular component one. So for that, we have the special case, the polarizing angle theta p, and for that we will meet one new law, which is the so-called Brewster law. So this British scientist discovered this relationship. So if we draw only the part here, which the component perpendicular to the plane of page, and that plane is the plane of incidence here. We extract that kind of plane here, and you see that the two reflected rays and refracted rays are perpendicular to each other. And the relationship between the refractive index of two materials and the polarizing angle shown by this formula. Yes, you can obey the Snell's law and then the relationship between the two rays here to prove that as well, in which theta p is called polarizing angle. So the so-called polarizing angle is the angle of incidence for which reflected light is 100% polarized. Okay. And A and B are the refractive index of two different materials. And the polarization also is useful in some application. And like last time, I showed you quite fast also the sunglasses as well. And we can see how the polarization of the light is used in this tools, this device, we can say. Oh, yes, this example you will do it at home is not so difficult. Okay, I want to move on the circular and elliptical polarization besides the linearly polarized and the unpolarized light. So here, showing you is the evolution, right? The change of the electric field over time. So from initial time t equal to 0 up to 1 cycle. So you see, we have the Cartesian coordinate x, y, z, in which x is perpendicular to your screen monitor, the screen, and then the light like propagate to our eyes in the x direction here. So this dot means that the vector is perpendicular to the page or to the slide or to your monitor, and then go to our eyes. And the two other axes, y and z here, y and z show the plane of your monitor. Yes, as we all look at the monitor now, right, the laptop screen. And the electric field vector at t equal to 0, initially it has this direction. So initially it's like this. So only along y direction, right? So we got the value EY at maximum. Here, after 1 over S of the cycle, so the electric field vector changed the position. And you see that in the clockwise direction here. With the two components, we can analyze in y-axis and in z-axis here. So now EY has this length and EZ has this length. So EY, we can say EY decrease in the length and EZ starts increase. So starting point EY max EZ equal to 0. Now we got this value. And then after 1/4 of the cycle, now the position of the vector E moves from the starting point here to this point, you see? And the EY component is equal to 0. The EZ component equals the amplitude, but in the negative direction, because the positive side is here, so that's why we got minus EZ max. However, it is at the amplitude value. Okay, that's the two here, the amplitude here. And also continue to the half of the cycle. You see, now EZ becomes 0 and EY becomes the maximum, the amplitude, but in the negative direction. That's why we have minus EY max. However, it's still at the amplitude. Only the sign here is positive or negative. So you see the evolution of the electric field vector, right, of the light. So from this point to this point, and then coming to this point, and finally this one. So the electric field complete one cycle, and you see here in the circle shape. So that's what we call the circular polarization of the light. If the light has the electric field and it oscillates in this manner, so that's what we call the circular polarization. And here, in fact, is a general case of the electromagnetic wave. If it moves parallel to the x-axis, like I say, so the propagation direction is along x direction, and the component E oscillate in this two Y and Z component like this one. So in this case, EY and EZ, we just analyze lags by they lag each other by a quarter cycle, or we say like 90 degree, right? 90 degree difference in the term of phase, or pi over 2 radian. And here we see that the amplitude of EY and EZ, the two components, are equal to each other. And finally, we got the magnitude of vector E is constant. That's why it can draw a circle. So vector E rotates in a circle in this case. And the circular polarization can be transformed into the elliptical polarization. So we see here the two components we need to consider is the EY and EZ, right? And also the phase between the phase difference between them. So this circular polarization can be transformed to the elliptical polarization. If the first case, the phase difference between the two component waves is not quarter cycle anymore. Here we have like 19 degree difference or pi over 2 radian phase difference. But it is like 45 degree or pi over 4, for example, and then the resultant wave vector will not rotate in the circular anymore. And or we can have the case in which the two component waves have different amplitude. So here, like not like the amplitude of EY and EZ equals to each other, but now they're different. So you can have the elliptical polarization. And you see here, we say the right circular polarization because it is also the electric field rotate in the right direction. Or we say, yes, and sometimes you have the left circular polarization, it rotates in the counterclockwise as well. we have the phenomenon or the property of the materials. Which is the bifringence. So in which for different polarization, the materials will behave different refractive index. So it can be used to have the phase lag between them as well. I mean, here I only show you the definition, but for the application of that, it can be used like for the phase shift later on, depending on different kind of polarization of the light, which incident to this material. And we have the photoelasticity. So the photoelasticity is that the when you have like the you applied the mechanical stress onto the materials, and then this can also have the bifringent property as well. So it can be used for in medicine as well. Okay. Wait a little bit for some questions. I also see in the chat box. I will answer you right after. Or we okay, I will answer you now. Những cô đang chưa nhìn thấy anh Hoàng Anh để cô nhắn cho anh Hoàng Anh một chút. Thì sáng nay anh Hoàng Anh để đợi cô một tí xíu nhé. Cô nhiều. Ok, anh Hoàng Anh lúc nãy mạng của chúng mình anh ấy vào hơi sóng tín hiệu hơi chậm, thế nên là bây giờ anh ấy mới thấy được. Ok, em mọi người check attendance guide. Trời đất ơi, Hoàng Anh đặt tên thật là cutie. So now we will move to the next phenomenon, which is the scattering of light, and it will help us to answer these following questions like why we can be able to, why we can observe with blue sky, or like when we see, we can at the sunset we see that red, or like why the cloud is white. Okay, so this due to one phenomenon called scattering. So scattering, yes, I can tell you immediately like this. It can be easier. Imagine you are in the space, and then there is no atmosphere, right? And in that case, we see only the dark color. It is what we also know. So the molecules, the molecules are very important in order to serve for observing some kind of color surrounding Earth. And the scattering, in fact, is a phenomenon in which the sunlight has been absorbed and then re-radiated in a variety of directions. So here, showing you here in these figures, is some situation of of a person who looks at the sky. Okay, we can see this one. So here's a guy who is enjoying the sun rays, and here's another guy who looking at the sun at some different moment in the day. So here we see the light from the sun, which is the unpolarized light, and also it consists of different kind of colors in the visual range, also the UV and the infrared and so on. However, for the visible, we know that the light of the sun composes of different colors. So this we say the white light, okay, here. And also with the unpolarized light is described by the random distribution of the electric field like this. So it propagates the light from the sun, propagates along x direction here. And then at this location of this man, he observed the above sky, for example, and we considering this point O, so in which this the electric charges of the molecules at the point O here will be affected by the electric field of the light, right? And then you can also analyze in two axes, Y and Z. And yes, the third one, Cartesian coordinate, which is X, we say the propagation of the light here. So these two in Y and in Z direction, we can analyze in these two directions here. And then, in fact, we can observe here that the sky is blue due to the fact that the air molecules scatter blue light more effectively than the red light. It is due to one law that the intensity of the color of the light scattered is proportional to the frequency power 4. So like we have the red and the blue. So we got like the 2H, the point or the wavelength is 380 nanometer and 760 nanometer. So we do this is the power number 4 and divide to them. We have like the blue light is like around like 15 times larger than the red light. In terms of that's why the blue is more dominant when the people look at this moment and the sky is blue. And for this observer sees reddened sunlight because after a long distance traveling, and then more or less most of the blue light has been scattered out. So that's why we have this. And pay attention also the scattered light that reaches the observer directly below O here is polarized only in the Z direction. Because what we also mentioned in the previous part, in the electricity and magnetism, the antenna, when it rotates in this direction, so the light will be propagated to the eye in another direction. So that's what, for the Y direction here, the polarization will not give the light to the people along the Z direction here. And yes, the question why the colors of the cloud is white, will look like white, why? I will leave you to think. And normally this kind of explanation question when they appeared in the test, yes, the test, not only you calculate the exercise, you do some kind of calculation, but also the phenomenon explanation. And also similar to the case, you drop some milk inside the water glass, and then you also see the color is white as well. So try to further reading and understand and explain this as well. Yes, very fast I show you also the two famous scientists, Lord Rayleigh and Sir Raymond, who contributes in the scattering investigation a lot. And also his name is named for some further application for SUS. As yes, you are in the ICT guys, so I don't tell you more about that. But if some of you in the morning class, like who will follow AMSN, for example, and these SUS applications is used a lot in the sensor. However, I just show you here, okay? Now, we will continue with the final section of this chapter in which we deal with some theory of about the light. Newton considered the light as the corpuscle, so a lot of particles. And then we have like also another consideration of the light, in which light is the wave. And Huygens principle also, like in the 17th century, more or less like in the period of Newton, he proposed that a light also travels and then has the wavefront, right? And then each point on this wavefront may be considered the source of the secondary wavelets here. So each point on this wavefront are considered as the source of the secondary wavelets. That means this point will generate new wavelet, you see. So, and that spread in all direction. Yes, in all direction here, with the speed equal to the speed of propagation of the wave. So if the wave had the speed of v, and then each point on this wavefront will spread the new wavelet, or the new wavefront there you see here as well, with the velocity of v as well. So you see here the ray in the ray of light in violet, and each point on this wavefront are the sources to make new wavelet, and then you have new wavefront here. So AA prime, the first wavefront, for example, or the original wavefront, and then we have the upcoming wavefronts, for example, BB prime, and then CC prime, DD prime, so on. Okay, so each point here make the new wavelet with the spherical one you see here, spherical one, and then the connection of all the envelope of that wavelet will make the wavefront. So it is the concept of the wave of the light, and the Huygens principle can be used to explain the reflection as well as the refraction. So the reflection and refraction are something very evident, very obvious for us now. However, at the 17th century, how it happens, they also trying to analyze that. So here we see the incident wave, the incident in violet color shows the violet arrows show us the incident rays, you see. So the wavefront AA prime, and then each point on A prime will act as the source to spread the secondary wavelet here in all direction. And then the connecting point, you got the wavefront the OB prime. And then similarly, each point on the wavefront OB prime generate the new wavelet, and then you have the wavefront NC prime. And the velocity that the points on each wavefront spread the new one is V, you see. So here you from the original point on this, it makes a new wavelet here with the distance or the radius here, Vt, you see, V times T. Because it's travel at the velocity of V, so after some time, T, you can make that kind of wavelet, and you got Vt here, etc. So due to the existence of the surface M prime, so the wave will be reflected like, okay, so here. So we say, oh, it bounces, right? So at the point O, you see also we got each point here will generate, and then you have the wavefront OB. Similarly for the wavefront NC. And the angle here theta A, and here's the angle theta R, for example. So this figure is too small, so we do the zoom in figure here. We do the zoom in figure on the right hand side. So AA prime is the wavefront, the original wavefront, and OB here, you OB prime, we have the next wavefront here. So the distance between these two wavefronts or we say the optical length. Optical path length. So we have here, in this case, is OP. So we draw the perpendicular line here, OP, and then we got the optical path length. And also for the reflection, we draw from A to the first wavefront we got here, OB, and then we see the distance is AQ. So OP and AQ, because the light travel in the same material, so the velocity is the same, is V. So OP and AQ equals to each other and equal to V multiplied by D. We got here. So if we look in this figure, a two right triangle OAP and OAQ, they share the same hypotenuse, OA, and they are right triangle. Also, you have AQ equals OP. So you have these two right triangles will be the same, right, with the same length. So for that, you can deduce the angle theta R and theta A equal to each other. So it is about the reflection. And now we will look at the refraction. For the refraction, yes, the reflection is the case in which the reflected rays and the incident rays lie in the same medium. And for the refraction, we have the incident ray like this. However, the refracted ones will be in another material or in another environment. And also you have, like, if you look at the light, it is bent, right? Yes, we got that. So now we consider the case in which the light travel in two materials, material A and material B, in which the refractive index, so for those who may forget, I would like to notice, always say the index of refraction. In this case, we got an A and an B, and for two different materials, and B is larger than an A here. So the light travels in material A with the wavefront AA prime. So it arrives at the boundary surface, or we say the interface between two materials, SS prime here, and then it when travels into another one. So wait a little bit, I need to Okay, so please continue. I'm so sorry, I have some interrupted work due to the Department of Academic Affairs for the admission test tomorrow. I'm so sorry. So here we are talking about the wavefront incidence in this material A, in the material A, and then it transmit in the material B with the so-called refraction, right? And now we're looking in detail, we zoom in this part. So the wavefront AA prime, and then it goes to the H point here when generate the wavelet, and then we have the new wavefront OB prime here, and the velocity of the light propagation in the A is VA. So we got the distance here, OQ equal VA multiplied by T. However, if we look at the material B, and then the optical path length in this case is only VB plus T. And we can see because NB is larger than NA, the refractive index of material B is larger than refractive index in material A. So this angle is smaller than this angle. Theta B is smaller than theta A. And also, as the velocity equals C divided by N. So we got the VB smaller than VA. That's why the distance AB is shorter than OQ. So from these two right triangles, you can deduce psi of theta A. Psi of theta A equals OQ, the opposite side, divided by the hypotenuse, so divided by AO. Psi theta B similarly is equal to the opposite AB, and in which AB is equal to VB times T divided by AO. And then you can make the ratio psi theta A over psi theta B equals VA over VB. You can mix the relation here, NB divided by NA following this formula, and then you got also it equals VA over VB. So finally, we have the relationship NA multiplied by psi theta A equals NB psi theta B is what we also have from the Snell's law. And one popular phenomenon, especially when we observe the object in the hot weather, like for example, my hometown is in Quảng for example, and when I drive from Hanoi to Quảng and in the highway, so like the road is very, the speed is high then, so you can see like in the hot weather, you see the vibration as well, sometimes of the water drop as well. And in that case, sometimes you can feel like you have some water before us, in front of our eyes as well. Or here, showing you in the desert, the camel. When this man look at this, we can feel like it is here in this case, right? So it is due to the fact that the different refractive index, of the different layer of the atmosphere. So it will change the direction. Here we got the refraction happening at different position of the air layers. So it is a so-called the ligage here. So it is some phenomenon we know so far due to this refraction, and we can explain by using also the Huygens principle as well to explain about the reflection and refraction. So here, higher up, the wavefront travels approximately straight. However, the hot air near ground has a smaller end than cooler air higher up. So light travels fastest near the ground, and thus the secondary wavelets nearest the ground have the largest radius V times T, and the wavefront thin as they travel. Yes, so you should pay attention on that as well. So for that, we end the chapter number 1 here. And now we will move to the second chapter, in which we deal again with reflection and refraction. However, we will deal with some concrete optical devices. So what we are going to do in this second chapter is to see how the image is formed by an optical device. So it's what we are going to do in the chapter 2, how an image is formed by an optical device. And we will deal with the reflection and refraction of the light at a plane surface or at a spherical surface. And in the spherical surface, we will deal with two types of spherical one, like the concave and the convex. So we have the term concave and convex. So pay attention as well, because it will decide the values of the radius and also like how the image is formed. And then the next part is about the refraction, in which we deal with the thin lenses, cameras, the eye, the magnifier, the microscope, and the telescope. So we end the chapter with the two different optical devices named microscope, which will help us to observe tiny things. So guys who work in advanced material science and nanotechnology or in life science, they enjoy the microscope a lot because it helps them to observe the microstructure, for example. And even we can have the optical microscope, is what we are going to study in the geometric optics. And however, we can use the electrons in order to have to work in the microscope, which we call the scanning electron microscope or the transmitting one. And the last one is the optical device, which help us to observe the star, right, the planet. So they are the setup of two, for example, two lenses, or you can also have like the reflecting case as well. However, we will study step by step all of them. So today, I think we can study together the first three contents, and then next class we will do the rest from 2.4. If we can be faster, it is better. Okay, let's go. And here is the suggested list of the exercise you should do to practice the knowledge in this chapter before the next tutor class of the next week, right? And the midterm tasks also include chapter 1 and some part we study today for chapter 2. I will see if we can do the midterm test next week or not. I will tell you later on next Monday after discussing with Dr. Hung, because initially we planned to have the midterm test on Friday, 25 March, okay? However, it should be happen if we have the offline class, because we prefer to have the midterm test offline instead of online. So we will have a look if the situation of the school change or not. We can come back to the university offline, or we still continue the online class. If we still continue the online class, so maybe we will shift the midterm test later on, because for the online class, or we can do a midterm test and online, and then we will see the result, and then we will decide. Because for the online, we really don't like that much. Okay, we will see. Basically, I want to note this with you. The midterm test will cover chapter 1 and chapter 2, and the precise date will be informed later on. Here we go. Now we will start with the reflection and refraction of the plane surface, which you already studied from the secondary school, in fact. So we will be very fast for that. I just want to make you, to bring you general concepts related to geometric optics, like the object. Yes, we need to observe something which is the so-called object, and then after using an optical device, it will bring you an image. So here we have the concept of object. Object is anything from which light rays radiate. So you need the light rays coming from that object so that we can observe that, right? So here we have this. So first we will see the two cases of the object. We have the first case If the light is emitted by the object itself, we call that the self-luminous. And the second case is in which the light is emitted from another source. However, the object is shined and then it will reflect the light from it. Okay, sorry, I will mute a little bit. So now we can sorry, we can continue. Có một bạn, cô xin lỗi cô chuyển tiếng Việt, vì có một bạn đang nói chúng ta bạn rất là theo dõi, đó là cô tuần sau cô lùi thi, cuối tuần bọn em thi 2 môn sẽ không ôn nổi. Ok, vì là các cuối tuần các em bây giờ đang thi lại, cô xin lỗi, đang thi hết môn, đang lại thi hết môn các môn nhất trí. Với cả là vì cô với thầy Hưng là muốn các em thi vào cái thi giữa kỳ vào tuần thứ 3 đấy, là vì cái buổi học, các cái buổi học 3 buổi thứ 6 đầu tiên nó sẽ là học mà đến tức là học 2 tiếng 45 phút ấy, còn buổi cuối cùng lại học dài quá, thì nếu chúng ta kiểm tra vào buổi cuối thì nó sẽ thành ra là hơi dài. Tuy nhiên là đấy, các bạn cũng có rất nhiều lịch thi. Thứ hai là chúng ta học online, xong rồi các em còn cần thời gian để ôn tập rồi còn làm bài tập, bởi vì đúng là lên đại học em học một buổi rất nhiều kiến thức đấy, nên là cũng bị rất là khó cho các em, chưa hề học online cũng rất là thiệt thòi nữa. Thế nên là với cả là cuộc thi midterm, thầy Hưng mà cô muốn là thi tự luận ấy, và thi trực tiếp chứ không phải là thi trên Moodle. Nhưng thế nên là nhất trí chúng tạm thời phương án đầu tiên chúng ta sẽ hoãn lại, và hoãn đến lúc nào thì cứ trước khi kiểm tra một tuần cô sẽ thông báo trước nhé. Ok, rồi nào, cô rất xin lỗi là có một số gián đoạn, bởi vì mai chúng ta tổ chức thi tuyển sinh và cũng có một số giấy tờ cô phải giải quyết, nên là cô phải gián đoạn một chút, cô xin lỗi các em. Now, so we will continue here. We see in this case we have the object point P, point P here, object point, which is the source of rays. So you see the incident rays at this plane mirror here. Okay, and then all these incident rays are reflected back. So we see the direction of the reflection here. So at this incident point, how we can draw? We draw the normal, which is perpendicular to the plane mirror here at this incident point, and then we draw the reflected rays. So this angle and this incident angle the same. Okay, so we can draw that these reflected rays here. So all of the reflected rays, we see that they don't indeed meet each other, but they seem to start at the same point, right? So in order to find the image, we need to find the intersection of these reflected rays. So that we will draw the extension line here. So that's why this part they draw with the dash. So pay attention, when we draw some line which is virtual, we can say, we will use a dash line here. So dash line here. So we got the intersection point of all the reflected rays. In this case, we have the virtual one, but in general it's called the image, right? The image is the intersection point of all the reflected rays. For the case of reflection, we will have the refracted rays. Okay, so here we got that. So the image point is an apparent source of reflected rays in this case. So light rays from the object at point P are reflected from a plane mirror. And then you find the image by finding the extension intersection of on these reflected rays here. We look on the right-hand side figures in which we have two different materials, Na and Nb. So first, the light travels and meets the interface between the two materials A and B. So for the reflection, the light will reflect back here. However, here we have the different materials B. So if we look in the material B, the light also propagates, right? The light propagates here in the material B. And due to the relation between the Na and Nb in this case, Na is larger than Nb in this case. So incidence will be smaller than the angle of refraction. So that's why you see it reflect. Then we observe the refracted rays here. Here. Our eyes is here waiting for the refracted rays to come, and then when you observe is the image. So the refracted rays don't meet each other, and also they have the virtual meeting point. So we make the dash line to find that intersection point here, P prime. So we got P is the object point, the source of rays, and P prime is the image point, which is the apparent source of refracted rays. So apparent only, you see, apparent, that means it's like seems to be the source, but here we have, in fact, it's not the source, right? So it's the apparent source of the refracted rays. So for the refraction by the plane surface, we see here the light rays from the object at point P are refracted from a plane interface in this case. And in order to draw that, we follow Snell's law. In order to draw that, we follow reflection law, okay? So because Na is larger than Nb, then so P prime is closer to the surface than P here, you see, yes. And the refracted rays entering the eye look as though they had come from the image point P prime, is how we observe the image. Okay. So our task is to find how the image formed, right? So for the geometric optics in general, what we are going to do is to find the relationship of S, the relationship of S prime, and R. I mentioned here S prime and R, and we say, okay, what are they? However, we will discuss in detail right after. So we will need to find the image location. So where the image is formed is our task when we use any kind of optical device to form any kind of image of any object. So we need to find the location of the virtual image P prime of object P formed by a plane mirror. Because what we are having here is the case of a plane mirror with both reflection and refraction. So we need to find that kind of position. So here, object P and the image P prime. So in order to find this image, at least we need two outgoing rays. So the reflected one, we can say in general outgoing rays. Okay, it's too hot. I need to turn on the air conditioner. So we need to at least two outgoing rays. So that we will draw two incoming rays at first. And normally we will try to find we will use some rays which is special. For example, you should draw the first ray incident to the plane mirror here, perpendicular to that. So because PB perpendicular to this mirror plane, and in order to find the reflected rays, very simple. We draw the normal, and then we draw also the reflected one. In this case, the normal will be perpendicular to the surface, and then it also coincide with the incidence ray. So it turns back, right? And the angle of incidence or angle of reflection also equal to 0. And we will draw also another ray here, an arbitrary incident ray with the angle of incidence theta, for example. So we draw an arbitrary incident ray, PB. The incident point is B, and we draw the normal here, and here is this angle theta. The angle theta with this arrow shows from the normal to the incident ray. So they also want to draw like this to, to remind you that the angle of incidence is formed from the normal to the incident ray. And then the light will be reflected with the angle of reflection equals the angle of incidence. So we got that. The two outgoing rays here is BP and B something like this. And we will find the image by making this extension of these two outgoing rays. And they actually don't meet each other. Here we have the virtual meeting point. So that's why you have the virtual image. Cô lại xin lỗi các em tại nhé cô. Okay, so sorry for this interruption. We can continue. So here we have the two incoming rays and two reflected rays here. As follows. PV is incident normally on the mirror. Yeah, so it is incident normally on the mirror. So we see how they use the term here. Because here you see the normal is also in the same direction with the PV, right? So we got the incident normally that means perpendicular to that. So it returns, the reflected rays here returns along its original path. And PV is incident at angle theta, okay, at angle theta here, or at the angle theta with PV as well. So this is two at the same position with the two parent rays at the same angle, and it reflects at angle equal with the normal, right? Theta here. And then the intersection between the two reflected rays formed the image. And because they don't meet each other, actually, so we got the virtual image. So in which we will have some concept. S is equal to PV is the object distance. So the distance from the object to the mirror. So we draw the perpendicular line here, the line normal to this surface, and then we got the object distance. Similar here, we have P from B as well. We have the image distance as well. So, and when the relationship between S and S prime is that the absolute value of S prime of the image distance is equal to the absolute value of the object distance. So here we also consider the sign of the quantity. So S prime and S here, they will be positive or negative, depending on some conditions. So we have the sign rules here I discussed with you, because we need to know when the objective distance or the image distance can be positive or negative. And then later on, we will study some spherical plane surface as well. Here is a plane surface, but we will study also the spherical surface. And for that, the radius of the curvature also can have the positive or negative sign for the concave and the convex spherical surface, for example. Because for these two types, the concave or convex spherical surface, the radius of curvature is positive or negative. So we need the sign rules so that you don't confuse about that. So first is the sign rule for the object distance. So when the object, with the object distance, it will be the values will be determined by the position of the incoming light. Yes, object, because it generates the incoming light. So why they will consider this relationship between the object and the incoming light. So when the object is on the same side of the reflecting or refracting surface as the incoming light. So here in this case, for example, we got here, the object is here, the incoming light is here, and the reflecting surface is here. So the object, yes, it is on the same side of the reflecting surface as the incoming light. So we got the object distance is positive, we have here. So in this case, the object distance is positive, otherwise it is negative. And for the image distance, so for the image distance, we will have the similar things. However, it will relate to the outcoming light. Okay, so in this case, we got the outcoming. And sometimes they also mention the outcoming or outgoing. You can use these terms. So when the image is on the same side of the reflecting or refracting surface as outcoming light, and then the image distance S prime is positive, otherwise it is negative. So here, showing you in this figure, the image is here, the outgoing is there. So they are in the different side, right? Different side of the reflecting surface. So that's why S prime is negative. So we follow this side rules for the object distance and the image distance. So you will know the polarity of S and S prime, positive or negative one. So here, for the plane mirror, in both of the okay, because they also consider the second case. So I will tell you also right now. We have the plane mirror and we have the plane refracting interface. Here between two different media. So we got the object and the incoming ray, and here the outgoing ray, and here's the image P prime. So for these both specific cases, the object distance S is positive because the object is on the same side as the incoming light. So for short, we can say like the same side as the incoming light. We don't need to mention also the reflecting or refracting surface because we know that we compare using this surface and this interface already. So that's why we got positive object distance. And here for the image distance, for these two specific cases, you see, both of them, we have the image is not on the same side as the outgoing. You see the outgoing light is here, the outgoing light is here, right? And the image is here, the image is here, while the refracting surface is here, the reflection surface is here. So that's why we have the negative image distance. So pay attention to the side rules, and then you don't make mistake. Don't make mistake in the side of the of different values we consider in the geometric optics. The last side rule, yes, is about the radius. However, before that, we see here for the plane mirror. For the plane mirror here, we got S and S prime has opposite value, right? They have the same magnitude, but different sign. So we got S prime equal minus S here. And for the radius of curvature of a spherical surface, like I mentioned, concave and convex spherical surface, for example. So the radius of curvature is positive or negative, depending on the position of the center of curvature with the outgoing light. So when the center of curvature C is on the same side as the outgoing light, so the radius curvature is positive, and otherwise the radius of curvature is negative. So also we have the side rule for the radius of curvature of the spherical surface, and we will look in detail in the upcoming session. I mentioned here with you here. And for the plane, the radius of the plane is infinity, right? When the sphere here becomes plane like this one, so from the values of radius of curvature, some definite values, to the plane it will become infinity. Okay. So now we will look at the image of an extended object. Before we mention is a point here, a point. Now we will draw for the extended object. So also it's the same. We just draw the, we just find the image of this point, and then we will find the image of this, and we do the projection, and then you got the image object. And because it is an extended object, so we have the concept of the height of an object or image. The height of an object or image is the distance from the head to the tail of an arrow. And pay attention, if it's in this direction, we got here y is positive, here y prime is positive as well, because it shows along this vertical direction. And by convention, we use in this textbook the notation y, because it shows the vertical direction along the y-axis. Or you can use h, like what you normally use in the high school or the secondary school as you want, but don't make the like with the dimension, I mean the direction of these two in the and the object. So if they show like here, so both value is positive, and sometimes you can have different direction for the image. So in that, negative values for the height. Okay. Because here we also follow the side rules as well. Okay. And when we use any optical device, so the optical device will change the height of the, we say like the change of the object, because what we observe is image. So by using that kind of optical device, the size of the object will change to the size of the image. So we have the lateral magnification concept, and here. Later on, you will have also the angular magnification. So here first, we will deal with the lateral magnification first. So M is defined by the ratio of the height of the image and the height of the object. So that is how the optical device changes the object, we can say, in the observation point. So in this case, we got y prime equals y. Sometimes y prime can be like minus y, or can be minus 1.5 y, for example, depending on the direction of the image compared with the object. And the image is erect if the image arrow points in the same directions as the object arrow. And in that case, because y and y prime will have the same sign, so M is positive, and the image is inverted, so we rotate it down. If the image arrow points in the direction opposite to that of the object arrow, so in that case, y prime will be negative, and you will have M smaller than 0. Yes, and I think it is easy for you to find the image of this object. So I don't tell you again. Okay, I will tell you very fast. You should draw the from Q from the head of the this you will draw the incident ray more to the surface, so it will reflect like this one, right? Okay, it turns back, and then you draw QV here. So we have VP here, this line, about this line, and you perpendicular, PV is perpendicular to the surface of the mirror. So you draw QV. So the reflected rays will be symmetric, right, to this incident ray through this axis. So you can find the reflected rays in this way. So the first reflected rays and the second one is here. So we will find the intersection point of these two rays, of these two outgoing rays, and then you find the image. Because they don't intersect with each other, actually, so that's why we will need the dash line here, and then you have the image here. Tour. So when we talk about the property of an image, we need to talk about first real or virtual, then erect or inverted, larger or same size, so I use here two terms. So I as the object property image formed by the optical device, and then we can describe the property of the image. If we have a system of mirrors instead of only one, as above, we have here mirror 1, mirror 2, and we have a point object P. And then observe here, yes, mirror 1 can form the image P1 prime of P. Mirror 2 also can form the image P2 prime of the object P. So we have P1 prime with P2 prime as the two images of the object P by these two mirrors, 1 and 2. It is also one way, right? Also, another way is that, pay attention, another card image. P1 prime is the image of P formed by mirror 1. However, we can access the object of the mirror 2. Why? Yes. The incident from P to the mirror 1 are here, and then it formed the image P1 prime here. However, these reflected rays of the mirror 1 also can strike mirror 2 and act as the incident rays as well. So, and then you see the reflected rays from the mirror 2 is here, and the image P3 prime. PT prime is the image P1 prime formed by mirror 2. So we can have like the image of object P formed by mirror 1, the image of object P formed by mirror 2, the image of image P1 prime formed by mirror 2. Yes, so you see. So an image formed by one surface or eyes in general, because here we have the plane mirror, but you can have also other cases for the lens system, for example. It can serve as the object for the second surface on device. So pay attention on that as well. Yes, it can be the image for this system. However, it can be the object for another one. Yes, it is. So we just deal with the image of a point or an extended object. In the case, it is formed by a plane surface. Now we will deal with the case of spherical mirror. So the spherical mirror, that means R is not infinity, right? R is some definite value. And for that, we will split reflection and refraction. Yes. So first we will the image of a reflection you learned from secondary school or high school as well. So it should be this part, right? So we have here the case of spherical mirror with the radius of curvature R and its concave side facing the incident light. So we have here the concept of concave and convex. So if you go to the ATM, the automatic teller machine, right? When you want to withdraw some money or you want to do some transaction there, so you will see some camera, and you see also the you see also some mirror as well, spherical one, but it's not the concave, it is a convex. Yes, and also like when you drive car or motorbike, normally it's more popular for the car. So the mirror on the two sides, also we have some smaller part of the convex mirror as well. So it helps you to observe broader, right, broader range. And for the ATM, it's help you to observe what happens beside you, behind you, like someone can go, it can approach you, or somehow it is the security function as well. So it is a convex, and here we mention the case. The first case is a concave. Okay, so here concave. like this one is a concave one. So, and when introduce you, even you already know when you study the previous education level, you know that for the spherical mirror, we have some basic concept. So we have here the concave spherical mirror. So in order to describe any spherical mirrors, there are some special points, or like we say, some basic points. So first is C, because it is the spherical one. Here you have the curvature. So C is the center of curvature. So that's why they draw here C, and you see here the radius. Okay, so you see center of curvature, C. The highest point on this curvature is called vertex. So we got the vertex of the mirror is at V here. So C, the center of curvature, V is the vertex. And also the line connecting the center of curvature and the vertex is called optic axis. Okay, so keep in mind this concept in English. Okay, in Vietnamese for sure you know so far. So we have the center of curvature, the vertex, and the optic axis. And here in this case, we have the point object located here. And in order to find its image, you need at least 2 outgoing rays, as I mentioned long time in this lecture, several times already, right? So here we will use one special ray, PC. So the first incident ray passing through the center of curvature and also the vertex, passing through the center of curvature and the vertex here. So it will strike the spherical surface. Also, we say like normally, right? So we also, if you draw the normal, the incident point is V, also the vertex point, and you connect it with the center of curvature C. So here it is the same with the optic axis. So the angle of incidence for this incident rays is 0, and the angle of reflection also 0. So it reflects back in this way. We got the first reflected ray. The second one we will draw, because the special points of the mirrors only C and V. Okay, so we will use another arbitrary ray. So the incident rays from P will strike at the spherical surface at point B. So we will form the normal by connecting B and center of curvature C. So BC is the normal. And the angle of incidence is theta, created by the normal and the incident ray. So the reflected rays will be symmetric to this incident rays. You got this line. And this reflected, the second reflected rays intersect the first reflected ray at P prime, and then you have the image. So you can draw the spherical mirror by using this notation, or you can use the line like what you usually did at the high school. Okay, you can do that as well, and then you have the 2 edge point to note that it is concave or it is convex. So we have, in order to form the image, we can draw PV passes through C, strikes the mirror normally. Okay, so it is reflected back on itself. So it is PV, and PB strikes at angle alpha with the axis. Here is the axis, and here is the angle alpha with the axis, and strikes the mirror at B, is reflected with the angle theta prime and theta is equal to each other. Okay, and we have the relationship alpha here plus beta here equal to phi. Yes, for the spherical mirror we have this relationship, and the two reflected rays intersect at the point P prime, which is the image. So it is easy to find the image by a spherical mirror. Here in by reflection, we call that the reflection, the spherical mirror. Okay. So you can draw in this way, like different incident rays and then reflected here, passing through P prime, which is the image position. This is what we observe. In order to be able to observe, that means the light coming to our eyes like this one. On rays from P that have small angle alpha passing through P prime, forming a real image. Because the reflected rays in this case, indeed they intersect. So that's why we have a real image. It is the first case. So we have alpha plus beta equal to 2 phi, and you can deduce 1 over s plus 1 over s prime equals 2 over r. You can do the mathematic transformation later on at home as well to prove that you have the object-image relationship here. So what we are doing in the geometric optics always is this stuff. You need to find the relationship between the image distance, the object distance, and the property of the optical device. So here is a radius of the curvature. Or then we will have the concept of the focal length. We will tell you right now.
Excuse me, can you go back to the last slide? Like, I just wanted to catch up. Like, what is the angle of alpha and beta?
Okay, we come back here. Here is the angle alpha here. The angle between the optic axis and the incident ray, alpha. And here is the angle beta here.
Okay.
Okay, yes. Because a lot, I mean, like there are quite many angles in this figure, so you can make you forget, right? Like I'm talking theta, and so on, and phi, and then you may, maybe forget that. Okay. So we have, yes, we can prove this relationship quite easy from geometric problem. So that's what we call the geometric optics. Geometric optics, that means we draw and then we use a geometry in order to solve the relationship it is. And here we have the concept of para-axial rays. So para-axial rays are the rays nearly parallel to the axis and close to it. So in that case, we have the angle alpha, like one student just asked, alpha should be small, right? And normally we will only consider that case. And in the case in which we observe like some big objects far away, and in that case we have the quite large alpha, and in that case you will face one optical phenomenon we call is the spherical aberration. And in this situation, the image seems to be smeared out. Yes, and in the area of the optics, some people want to fix this issue as well. And we will also see this kind of fixing in the next chapter. We will deal with that later on, like how we can fix the spherical aberration to have precise image. We will also study in the next part. We have some figures in this slide here. So we have the two cases first. I will discuss with you about these two cases first. The center of curvature, C, center of curvature, C here. And you see these two spherical mirrors are different. The first one is the concave we just discussed. And the second one here, we see the shape like this one, and the black solid curve or the black solid line show us the spherical mirror. In this case, it is convex, right? So the center of curvature is in this location. And the object point P here, the injected or the incident ray. And when it strikes at the spherical mirror, it reflects in the outgoing rays like this one, reflect, and we have the outgoing ray like this one. So coming back to the sine rule for the radius of the curvature, I remind the radius of the curvature is positive or negative depending on the location of the center of curvature and the outgoing ray. So in the first case, the center of curvature is on the same side as the outgoing ray, like here as well, right? We compared with the surface of reflection. So in this case, they have the same side. So that's why we have the positive radius of curvature. Second case, the center of curvature is not on the same side of the reflecting spherical surface as the outgoing. The outgoing is here in this side, and the center of curvature is here on this side of the reflecting surface. So the radius is negative. So like what you learned before, like, okay, the concave spherical mirror, you have positive radius of curvature. The convex spherical mirrors, radius of curvature. And now we want to discuss with you in detail so that you understand which sine rules we use to have this kind of assumption. If you don't like that, you can assume, I mean, you can make a new assumption like, okay, I don't like that. I want the convex mirror in which the radius will be positive. Okay, you change the conventional word. However, we have also, like in physics, normally you need some kind of convention in order to make the consistency of all the people to explain or to describe any phenomena. Okay, here. So these two figures is to explain to the two cases of the spherical mirror, concave or convex, and about the size, the sign of the center of curvature and the values of the radius of that. Okay. And now we will, yes, it is to fix that. We will have also the concept of focal point and focal length. So for the concept of focal point, so we can imagine immediately focal point is a point at which the light is focused, right? So here we consider a parallel incident rays like this one. So they start from the object which is located very, very far away. So as the object distance is at infinity, and then the incident rays strike the spherical surface, and then they will be reflected like this one. And we can follow this formula. And then when you see S is infinity, so 1 over S goes to 0. So 1 over S prime equals 2 over R. Or we got S prime equals R over 2, divided by 2 here. And we call this value is F, which is the focal length, because the light is focused here in this case. And in another manner, if we put the object as a focal point, and then we inject the light to the spherical mirror, so the light will be reflected like this one. So, and we see that the reflected rays are parallel to each other and parallel to the optical axis. So if S equal to R divided by 2, and then you replace into the formula, we got S prime equals infinity, right? So in this case. So we have the concept of focal point, and the focal length F equals to half of the radius of curvature. And then you can write the object image relationship 1 over S plus 1 over S prime equals 2 over R or equals 1 over F. And it's also one way we usually use for the upcoming part, like for the lens as well. So the relationship between the object distance, image distance, and the focal length of the optical device. Or we use the radius in the case of the mirror as well, when help us to describe how the image is formed at which location. Okay. Now we will move to the case of the extended object. So before it is a point, and now we will move to the case in which the object is an extended object here. So in order to find the image, you will find of this object, you will find the image of this point, this Q, the point Q, and then we do the projection. We got the image of this object. So we have the spherical mirror here with some special points C and V, and also F as well, right? Now we don't use that at once. We will use that in the final part, but we got this point. So you draw first the incident ray from Q passing through the center of curvature C to this spherical surface, and then it also the normal, right? Because it is C here and this incident point here. So the ray is reflected back in this way. So you got the first reflected ray. The second one, you draw Q and QV. So V is the vertex. So you draw the incident ray from Q and pass to the point of the vertex here, QV. So the normal is the optic axis BC here. And then you can draw the second reflected ray here. So the first reflected ray and the second reflected rays intersect at this point Q prime, so that you have the image. And then you see here in this case, for example, the image has a different direction, right, compared with the object. So we call the image here is inverted. And in this case, Y prime is negative. Yes, they have some mistake in the text here. It should be M equals Y prime divided by Y instead of Y divided by Y prime here. And we can use these two right triangles to deduce that the relationship M equals Y prime divided by Y, which is the original definition for the lateral magnification. And in this case, it is equal to minus S prime divided by S, in which S prime is V P prime here. It is the image distance, and S is VP, which is the object distance. And in this case, both S and S prime are positive because the object is also the same side as the incoming rays, right? And then you got positive S. The image also is in the same side of the spherical mirror as the outgoing rays. So also you got S prime positive. Also the center curvature of the concave mirror, you see here, the center curvature is on the same side as the outgoing rays. So it is positive as well. And we see we have, in this case, the image is real, inverted, and smaller than the object. Yes. So we have this lateral magnification for the case of the spherical mirror for the reflection phenomenon. We have this example, and I just want to discuss with you to analyze the information inside this example here, which is an example related to the image formation by a concave mirror. Yes, we have like some examples. So here they denote with one. A concave mirror forms an image on a wall 3 meters in front of the mirror, and a headlamp filament 10 centimeters in front of the mirror. So if we read this, and when we do the geometric optics, please make a draw like this one. Yes, we should draw because we are in the geometric optics, and especially when you're doing some physics exercises, you should draw, you should write down as well. Not only replace the formula and then you have the result, but also to draw, to illustrate the phenomenon. It is what in the physics world. So here you have the on a wall 3 meters in front of the mirror. So you draw the mirror here, and also you draw that kind of wall. So it is a screen to collect the image, and the distance between them 3 meters here is the object, sorry, the image distance. So S prime equal 3 meters. It is the image of a headlamp filament 10 centimeters in front of the mirror. So the headlamp filament should be here, and it is the object. And you have the distance S equal 10 centimeters here. So you have S, you have S prime. You know the location of the object, you know the location of the image. And what they ask you to find is the radius of curvature, so R, and the focal length of the mirror. So they ask you to find R and F. So in order to do that, you just follow the formulas which show the relationship of the object distance, image distance, and the radius of curvature of the reflection of the spherical surface. So pay attention, only for reflection, we have this formula. For refraction, we will have different formula. Okay, so pay attention on that. The question D, what is the lateral magnification? So lateral magnification M is equal to Y prime over Y. It is the original formula, or we say for definition. And then in the case of reflection of spherical surface, we know M equal Y prime divided by Y, and equals minus S prime divided by S. So you can find the lateral magnification, and then you can find also the image height. So due to the limitation of time, so I also mentioned, I discussed with you on the solution as well. Next time, if we have like enough time for different examples, I will also ask students for discussion, and then you will gain bonus point like what we did in the previous lecture. But today we don't have so much time, so that's why I speed up a little bit for that. So we just study the reflection of spherical surface, but for the case of concave spherical surface. So now we will deal with another case of the spherical surface. So we can say the name is concave spherical surface, or concave surface is okay. So here we deal with the convex mirror here. So for that, we look at the center of curvature is here. And here is the object, the point object, and the incident rays like this one, and the reflected. Now I don't need to tell you in detail anymore, right? Because it's clear that I think you can immediately draw them. So the normal here, because B is the incident point, so you draw the normal passing through the incident point B and the center of curvature C, and you got the normal, you got the reflected rays here for this incident ray PB, and for PV it reflects back clear. And in order to find the image, you need to find the intersection point. So these two reflected rays do not meet each other, so you need to draw the extension line. So that's what you have the dash on here. and you have the P prime is the virtual image. So in this case, we employ the sign rules, and then we have the S equals PV. The object distance is positive, right? Because the object and the incident rays are at the same side. Okay, you got the positive S, and S prime here is negative because the image and the outgoing rays are not at the same side. So now everything is clear, right? So, and also the incident ray here created with the optic axis an angle alpha here, and beta is the angle between the optic axis and the reflected rays we consider. So we got alpha, beta, and the angle at the center of curvature we got 5, and we will have the relationship M equals Y prime equal over Y equals minus S prime over S. We can prove that as well. And here for the case of the point object, and similarly we have the extended object right here, PQ. We can also draw the incident rays from the point Q to these mirrors. This one is the convex one, and then we find the reflected rays here and here. So we should use the special case in which the incident ray passes through the center of curvature, so it reflects back, because it's the same with the normal. And then here the symmetric reflected rays, right? So you find the image Q prime, P prime. And then we have, so the same with the case of the concave spherical mirrors, we have also M equals Y prime over Y, which is the original definition for lateral magnification, and equals minus S prime over S. So we have here the same relationship as well, okay? And for the case of convex mirror, the focal point F is not really like we have for the concave mirror, because if you inject the parallel rays like this, corresponding to the object at infinity, so the reflected rays will be presented as shown in the figures, and they don't intersect, right? So we draw the extension line, and then you see they meet at the point F here. Is called virtual focal point. Yes, because it is the virtual point, right? Which is behind the mirror we have here. And S equal to infinity, so the image distance S prime, for the case we consider the object is very, very far away, equals half of the radius of curvature, and equals to F, which is called the focal length. And if we put the, if we inject the incident rays, which seems to meet at the focal point here, and then the reflected rays are parallel. So if S equal to half of the radius of curvature, or equals to the focal length F here, we have the values of the image distance is at infinity. We got here S prime equal infinity. And in this case, you have the virtual image. Right, you have that. So sometimes you can have some exercises in which they tell you we have a virtual image, virtual object. So don't worry. You can easily make this figure in that case. Okay. So the focal length also F equals half of the radius of curvature. And normally we use also 1 over S plus 1 over S prime equals 1 over F here. In general, for two cases of spherical mirrors, we will use the graphical methods in order to draw easily, right, the rays of light, and in order to find the image. So we have the object PQ here in front of the spherical mirror. So here is a concave mirror, and here is the convex mirror. And the center of curvature of the concave mirror is here, also in the same side with the incoming rays. And the center of the curvature of the convex mirror is here, not in the same side or in the opposite side with the incident ray, you see. So that's why you have here positive radius of curvature and here negative radius of curvature. We have 1, 2, 3, 4. So we have 4 special rays, incident rays. So the first rays here, if a ray parallel to the axis, here means to the optical axis or the optic axis as well. So for the concave mirror, it is reflect through the focal point. And here, the focal point is here, and which is virtual. So in fact, it reflects and it doesn't pass through the real point here, right? So we have, it passes through the focal point for the case of the concave mirror, but for the convex one, it appears to come from the virtual focal point of the convex mirror. Yeah, so pay attention to the way we draw for the two cases of the two types of mirrors. And for the second rays, a ray through the focal point in the case of concave mirror, or a ray proceeding toward the focal point F for the case of convex mirror here. It is reflected parallel to the axis, here. The third ray, a ray along the radius, because we got here the center of curvature point here, C. So if it passes through the center of curvature, so here we got the center of curvature. Here the center of curvature is behind the mirror, like this one. So the light strike the surface at this point, but it can't penetrate through that surface, right? So only we say the light ray along the radius, we see here. It went for the concave mirror, it went intersect here. It intersects the surface normally, right, and is reflected back. So here, through away the center curvature, see, it will reflect back along its original path. And for the fourth case, a ray to the vertex B. Here, the two cases. So it is reflected and forming equal angles with the optic axis. Or we say like it reflects symmetrically to the incident ray. So here you have this angle will be the same for these two, and the optic axis acts as the normal in this case. So it's how you can find the image, or you can draw the reflected rays when the light rays strike the spherical surface for the two cases, concave and convex mirrors. So for that, we have one example here. The concave mirror with different or with various object distances. So we will consider the concave mirror has a radius of curvature with absolute value 20 centimeter. So pay attention when you read the problem and you see the absolute value 20 centimeter. So pay attention if it is concave. So the radius of curvature should be positive. But if it is convex mirror, so the radius of curvature should be negative. Yes, so pay attention on that. Find graphically the image of the object in the form of an arrow perpendicular to the axis of the mirror at object distances of A 30 centimeter, B 20 centimeter, D C 10 centimeter, and D 5 centimeter. You can use S or you can use D for distance as you like. Okay, don't worry about the notation. And then they ask you to check the construction by computing the size and the lateral magnification of each image. So what they ask you is to draw, right? You draw the graphic location, right, of the image and the object as well. And then they also want you to confirm if you do well or not by employing the formulas as well. 1 over S plus 1 over S prime equals 2 over R or equals 1 over F. So I will immediately show you the different graphical setup for that. So here we have the spherical mirror. In this case, it's a concave mirror. Here's the object. So, and here's the center curvature. So the first case, we got R equals 20 centimeter and positive because it is the concave mirror in which the center curvature and the outgoing rays are on the same side. Okay, well noted. Okay, and then the object distance is 30 centimeter. So it is located here. So you will find, you can use only 2 among these 4 special rays of light, and then you can find the image. So in the first case, we see the image is real because it is the real intersection of the outgoing rays, smaller than the object and inverted, right? The second case, when the object is located right at the point of the center curvature. So by drawing, you can also find that the image also at the same location, inverted and same side, right? And real as well. And now if we shift the object at the point of the focal point here, so the image is at infinity. And then if we shift the object closer to the surface, in that case, the image is virtual, erect, and larger than the object. You see here. Yes, you can draw it later on as well at home to do that. Now we will move to the next session in which we will deal with the refraction at the spherical surface. So we just stopped the reflection at the spherical surface, and now we will deal with the refraction one. So which is quite new, not really new. It's what you already studied earlier. However, we will deal with this phenomenon now. Before we move to this session, I propose to have like a couple of minutes break. So we will start now. We have like, we will break until 10:03. Okay. I do hope that you feel less tired after like a short, a quite short break. Okay, so now we will come back to our lecture. We are discussing the image of a point object at a spherical refracting surface. So what we just studied in the section 2.2 is the case of the reflecting, yes, the reflecting surface, the spherical reflecting surface, and now we move to the spherical refracting surface, which split the materials. Here we see material A and material B. So showing you in these figures, we can see a spherical surface with the radius r. Okay, so the radius of curvature r here, and there are two materials, and A and B refractive index, right? And if we have the object, the point object P here, in order to find the image of this object, we will draw the incident rays. So we will draw only two incident rays for simplification. You can draw more, however, we can put at least two rays here. So the first incident rays we choose is the something like quite a special one. We got BB. So the first incident rays along the optic axis. So the normal will be also the same direction, right? The same line. So you have the refracted rays also in the same direction, but in another environment. The difference between the refraction and reflection is that refraction, that means the outgoing rays and the incident rays are in two different media. And for the reflection, the outgoing rays also in the same medium with the incident rays. So here you have the first one, the first refracted rays, or we say the transmitted ray here. The second incident rays to this spherical surface here, at this point, you draw the normal BC also. So this normal here, and then you draw the refracted rays. And due to the relationship between the refractive indexes of two materials, NA is smaller than NB, so we use Snell's law. We see that the angle of incidence theta A is smaller than the angle of refraction theta B. So you can draw quantitatively this direction. You got this direction. So the intersection of two refracted rays here is at this point. So this point is the image, and they intersect. Actually, so you have the real image. Yes. So in this case, we have S prime, and also R. All of them are positive. So the object distance is positive because the object is located in the same side as the incoming rays. Yes. So, and so we have positive object distance. For the image distance, we see the image is located also in the same side of the refracting surface as the outgoing ray. So you have positive S prime as well. And the central curvature of this spherical refracting surface is on the same side as the outgoing ray as well. You see, so also you have radius of curvature is positive. That's why I emphasize with you the sign rules, because if you understand well the sign rule and you understand the reflection and refraction, even they are very popular and they are easy for you. But when we know well them, and then all the other optical phenomena you will feel very easy. Yes. So here we have the formation of the image, and we have here the angle theta A and angle theta B, also the angle alpha, angle beta, which are the angles of the optic axis and the incident ray, and the optic axis and the refracted rays respectively, and find beta. And phi is the angle of the center curvature here. So we need to find here S and S prime. I note with the question mark. In fact, it is a relationship between S prime, and also R. Yes, we need to find out. Here we have the image P prime of P formed by refraction at a spherical surface. And in this example, the refractive indexes of two materials are NA and NB. And in this case, even they don't mark NA smaller than NB, but if you just look at the figure, you see the relationship between the two angle of incidence and angle of refraction. And if you focus well on the lecture, you know that if theta A is smaller than theta B, larger than theta B, that means NA is smaller than NB. Okay, all of them are consistent to each other. So in order to find the image, we will draw here, as I just discussed with you, we draw the PV, strike the sphere, so it passes straight into the second material. PB is incident at angle theta A, it is refracted at angle theta B. Okay, so these two refracted rays intersect at P prime, and we have the image P prime. And as the object distance equals to PV, the distance from the object point here to the vertex of the mirror, I'm so sorry, to the spherical surface is not a mirror anymore. In this case, we have the spherical refracting surface, so the vertex point here. And S prime is the image distance, which is the distance from P prime to the vertex point here, or P prime B. This time we will do the mathematical analysis a little bit to form the relationship between S and S prime and R, and also it's related to the two materials, so also related to NA and NB. So we will consider the triangles PBC and P prime BC. Yes, we consider these two triangles because they consist on the angles we are considering. So you see here first, if we look at the angle theta A at the point B here, we easily see that theta A equal to the sum of these two angles, alpha plus phi, right? And also if we look at the triangle P prime BC at the point C, at the edge C, we see that phi equals theta B plus beta, okay? And now we follow Snell's law. We have the relationship between the refractive index and the angle of incidence, the angle of refraction of the two materials. We have NA times sine theta A equals NB times sine theta B. And normally we will consider with small angle alpha, small angle theta. So when the angle is small, what you know from mathematics is that sine of that angle and also tangent of that angle more or less equal to the value of the angle. But in radian, pay attention, the unit we use should be radian instead of the degree, right? So you can deduce NA multiplied by theta A equals NB multiplied by theta B from the Snell's law. And we can deduce theta B equals NA over NB multiplied by alpha plus phi. You deduce that, and we do some kind of transformation. You got NA multiplied by alpha plus NB multiplied by beta equals NB minus NA multiplied by phi. And now if we look at this angle alpha and angle beta more closely, we see tangent of alpha, so equals to the opposite is h here from this point to the optical axis, and we have also delta is the distance from V to this projection point. So we have tangent of alpha equals h over p, this length, right? So s plus theta, and tangent of beta equals to h divided by s prime, the image distance, minus theta, minus delta, so sorry. And tangent of phi equals h divided by the radius r minus delta here. And normally also we have the condition for theta is small, so you have tangent of theta more or less equal to theta. And on the angles here also you have the delta is small as well. So all the angles are small as well. So you can deduce alpha, alpha equals h over s, beta equal h over s prime, and phi equals h over r. And now you replace to the previous formula, and then we find and do some very short transformation only, and then you can find NA over S plus NB over S prime equals NB minus NA over R. So here is the image and the object relationship, right? So we got the object and image relationship by a spherical refracting surface. So pay attention, the object and image relationship S and S prime will be related to each other in different cases, depending on the optical device we use. Before is the plane surface, or the spherical reflecting surface, or here the spherical refracting surface. And when for the refracting surface, for sure the material properties will be affected to will affect to this phenomenon. So that's why we will concern also the refractive index of the materials. And if we see like Na corresponding to S, the refractive index of the material, which include the incident ray or the object, here we got Na in the numerator and S in the denominator, and NB the second material. So it corresponds to the image distance. So it's the way you understand how this formula can be achieved. And then in order to learn by heart, to employ it, you will need like the understanding for sure, and then also like the proper way to easily keep it in your mind. So I would suggest that you see the refractive index corresponding to the object in the same, right? So this material and the object is also in that material. See here, the image in the second material. So we got NB over S prime. And on the right hand side, in the numerator, you got the subtraction of the two refractive index, or we have here the difference between them. And in the denominator, you have the radius of the refracting surface here, the spherical refracting surface, and then you got that. So here we have for the case of a point, and now we will move to the extended object. So for the extended object with this height, in order to draw the image here, also it follows as our previous steps. We choose the head here, right? The head point Q. And in order to find the image, we will draw here the incident rays at this point V, the vertex point. And then because NA is smaller than NB, so the angle of refraction is smaller than the angle of incidence. So the light will be bent in this manner. So you got the refracted ray here. And for the second incident rays, you should choose which should also pass through the center of curvature. So we choose this second incident rays. So the refracted rays also passes through the center of curvature. And we have the intersection of two refracted rays, right? So you got here Q prime is the image of the point Q formed by this spherical refracting surface. And as we can see, these two refracted rays intersect actually. So the image is grilled, inverted, because you see the direction here of the object in the image, so it is inverted and smaller than the object. You see, yes. And the angle theta A, theta B here. And also we can we can find the lateral magnification. In the case of the spherical refracting surface, M equals y prime over y, which is the original formula. And in this case, it is equal to minus NA multiplied by the image distance divided by NB multiplied by the object distance. Yes, so we will prove that, yes, a little bit. So you have P prime Q prime is the image of PQ, yeah, okay. And we draw QV here, strikes the sphere at angle theta A, so it is refracted here. It refracts at angle theta B. And also during the drawings of some recent figures, always we also draw the arrow here to show how the angle is generated from here, the normal, right? And to the incident ray, we got theta A here. And from the normal to the refracted rays, you got theta B. You can use this type arrow or not, but they show the arrows here to emphasize with us how these angles are formed. QC is incident to C, so reflects along C. Okay. So you can pay attention as well for the what they use for the reflection. So the incident rays, they strike the surface, for example, but they will be reflected back because here is a reflecting surface. So that's what we don't have the transmitted rays. So for that case, they don't use like the QC, for example, incident through C in the reflecting case. Yes, for the reflecting case, because the light in this case incident to the interface, and then it transmits to the second materials. So that's why they also write here. QC is incident through C, so and reflects also along C. It is. And these two refracted rays intersect at Q prime. And you got the image Q prime, P prime of the object QP. We just discussed. And now we will see the relationship of the height of these two objects and image, y and y prime, as well as the angle theta A, theta B, and the refractive index and A and B. So in order to do that, we want to know how the spherical refracting surface change the size of the object. So we need to see the relationship of the two heights here. We consider the triangles. They are the two right triangles, PQV and P prime Q prime V, because we have this side with the height of the object and the height of the image. So they have the tangent here, tangent of theta A equals the opposite divided by the adjacent. So you got tangent of theta A equals y over s, tangent of theta B equals y prime over s prime, and also to denote with the minus here. Yes, because it's also the direction, due to the direction. So you got minus y prime over s prime, because the direction of P prime Q prime in this way, that means y prime is negative, and that's why they put also the negative of negative to make it positive for this angle. And we obey Snell's law. So you got NA multiplied by sine theta A equals NB multiplied by sine theta B. And as usual in physics, we will follow some approximation from mathematics, right? So we consider theta is small, very small. So tangent of theta is approximately equal to sine theta. and also equal to theta as well. So we can deduce that NA multiplied by y over s equals minus NB multiplied by y prime over s prime. And you can deduce the relationship here. You got the ratio y prime over y will be equal to minus NAS prime over NBS with the minus here. So it's how we can prove that a lateral magnification formula in the case we got for the spherical refracting surface. Yes. So the lateral magnification in the case of spherical refracting surface. So pay attention, the refracting and the reflecting also will be different, okay? Now we will find the image if we have the plane refracting surface. Yes, so we just discussed the spherical refracting surface. And now if we move to the plane refracting surface, so the plane is a special case of the spherical surface in which the radius of curvature comes to infinity, right? When you consider a very big surface and then it will come to the plane. So in that case, we got here R goes to infinity. And if you replace to the previous formula, okay, it's a little so far away, so I don't come back. I will write in the chat box. So you got NA over S plus NB over S prime equals NB minus NA divided by R. So sometimes I use the parent chi, sometimes I don't use that. Don't make it so complicated, but you should pay attention. NA here mean N and subscript A, not N multiplied by A. So R goes to infinity. So on the right hand side, this ratio goes to 0, the limitation. So you have NA over S plus NB over S prime equals 0, right? So from that, you can deduce the lateral magnification, which is equal to minus NAS prime over NBS, which will be equal to 1. So pay attention on that as well. Here we go. So same lateral size and erect. Okay, for the plane refracting surface. Now we will have one small example related to the image formation by refraction. So in this example, we have here a cylindrical glass rod which has index of refraction 1.52. So last lecture, we consider also the list of refractive index of different substances in which the glass can have the refractive index varies around 1.5 something. I also discussed with you. So here we have the case in which the value of index of refraction is 1.52, and it is surrounded by air. One end is grounded to a hemispherical surface with radius r equals 2 centimeters. A small object is placed on the axis of the rod, 8 centimeters to the left of the vertex, and there are two questions. First, they ask us to find the image distance, and then they ask us to find the lateral magnification. So it is the traditional questions related to geometrics. Always, you know S, you need to find S prime, and also M. You know M, and you know something, you will need to find S and S prime. It is the relationship of these parameters. So we see here in this figure. You will do this exercise at home. However, I would like to analyze this with you together to be, faster. So we have here the glass rod, and one side is hemispherical. Here, we got C, the center curvature, with the radius of curvature R here. R is equal to 2 centimeters. And the refractive index of the glass is 1.52 NB, and surrounding it is air, is 1. And the object is placed on the axis of the rod, and also in air as well, right? 8 centimeters to the left of the vertex. So here we have this, so the left of the vertex, here the vertex point to the left. Yes, so we got the distance of the object distance S equals 8 centimeters. Center of curvature here, and we can find the image. So we draw the incident rays from the object P. So, and one is a special case which incident through the center of curvature. So it also refracts in the same direction. Okay. We choose also another arbitrary rays incident here, and then you can draw the normal right here. So from this incident rays, you connect with the center of curvature, you have the normal. And as the incident ray is in air, lower refractive index than the material B here. So the angle of incidence should be larger than the angle of refraction. That's why you can draw this refracted ray like this one, similar to this as well. And then the refracted rays gather at the point P prime, which is the image. So we see the image in this case is also real, right? So the image is real. We don't know that longer, sorry, larger or smaller or erect or not. We need to solve the equation as well, because here is a point. If you draw the object and then the extended object, you can easily see, but and it will be in the next session. However, the important thing is that ring, and then ring, you should be go with the inverted one, and should be smaller as well. We will see in detail is it true or not by following the formulas. We use this formula NA over S plus NB over S prime equals NB minus NA over R. And then very easy, you just replace all the other quantities, and then you can deduce the value of S prime. And for the lateral magnification, we employ this formula M equals Y prime over Y equals minus NAS prime over NBS. And then you can find the values of the lateral magnification. With this value, so lateral magnification is negative. Negative, that means inverted. The absolute value of M is smaller than 1. That means the image is smaller than the object. It is what we conclude. So when you find the values, and then it is also more professional if you write a short description about the image. The image is real, yes, because S prime is positive here, smaller than the object and inverted. Okay, here we go. We can, yes, okay, cool. So for that, we finished the session 2.3 of the refraction of the spherical surface. And I don't want to move to the 2.4. In fact, so we will, stop the lecture today here, because this morning also we stopped at 2.4. So I want to have the homogeneity between you two classes. So I will spend some time discuss with you about the midterm test a little bit, and then we will end the lecture today here. Thì chúng ta sẽ tạm dừng bài ngày hôm nay ở đây. Rồi cô cứ sợ là không bị không kịp thời gian, với cùng rất là ổn. Các em có hiểu bài không? Some yes, some no, no one. Okay. Còn bạn Nguyễn Thiên Ân, thank you, I'm super tired here. Cô cũng hoàn toàn thấu hiểu cảm giác khi các em ngồi học on các cái lecture lý thuyết ấy, xong rồi nghe giảng viên thao bất tuyệt, xong cũng cảm thấy mệt, rồi còn đang choáng rồi cô ạ. My records got break due to buffer, probably my back's hurt. Okay, cool.
Could you upload the slide before we study?
Yes,
so we could read it before the class starts, so we will maybe understand more about the lecture.
Okay,
yeah.
okay.
I don't understand what you just said.
Okay, yeah. I agree. So today I will upload the chapter 2 and also chapter 3 already, and also I can also upload chapter 4 as well. Yes, and then you guys can read before we have the class, and also I think is helpful. I totally agree. Yes. And about the midterm test, I will inform you later. So do you guys like the online midterm test? Các em có thích bạn làm bài kiểm tra online cho giữa kỳ không?
Yeah,
Online.
yes.
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 Các em thích làm bài trắc nghiệm, các em thích bài tự luận.
MCQ.
Ok, bởi vì chắc ít nhất là làm bài MCQ chúng ta có hết cả các đáp án một cách ngắn gọn đúng không? Online but not like thermal. Thế vấn đề gì xảy ra với cả thermal thế? Cô cũng thermal có vấn đề gì xảy ra khi các em làm online? Khó quá hay là như nào?
Yes, that's kind of hard.
Kiểu thermal nó sắp xếp câu hỏi
thermal nó vừa ít nó vừa khó của cho có mỗi
có
20 phút ấy, nếu em nhớ không nhầm, trung bình một câu 1 phút mà đề khó
đầu thì nên là cũng mất nhiều thời gian.
Đặc trưng của thermal dynamics thì thông thường các em sẽ có rất nhiều đại lượng, tức là phần bài tập cũng sẽ hay dài, xong rồi nếu thời gian mà ngắn thì các em cảm thấy hơi khó đúng không? Khó và dài không kịp. Ok. Thế còn là thầy Hưng và cô thì định là cho phần kiểm tra midterm tụi em ấy, gồm có 1 tiếng. Thì 1 tiếng và 2 đề sẽ nằm trong cùng một buổi thi thôi luôn nếu thi offline. Em đang khóc tiếng bán vì electricity and magnetism. Cô không dạy phần thermal nên là cô không hỏi, nên cô có một câu hỏi của bạn nào đó là không cho sẵn các giá trị như nhiệt sinh riêng, và cô thì phần qua này mình không có liên quan. Thế nhưng mà bao nhiêu câu thì còn tùy vào hình thức thi, chẳng hạn như là nếu các em mà thi tự luận ấy, thi tự luận và thi trực tiếp, làm bài trực tiếp thì số lượng câu sẽ khác. Bởi vì lúc đấy mình sẽ giải bài, mình sẽ viết các thứ. Thế đúng chính xác, cô rất là concern cái việc là cheat hay không cheat đấy, chính là chỗ đấy là tại sao mà việc mà thi online hay offline, bởi vì lớp chúng ta có 2 TA, đó là anh Hoàng Anh và chị Hà. Các anh chị sẽ cùng với các thầy cô gọi là coi thi, thì nó sẽ tốt hơn. Và hội trường chúng ta bây giờ rất là đẹp, rất là xịn, cô cũng rất thích là các em đấy coi thi cùng với anh ở đấy. Thế còn nếu thi trắc nghiệm thì số lượng câu thông thường ấy, thường sẽ để ở góc độ là khoảng tầm, các em có 30 phút cho phần optics, cô ví dụ thế nhất trung bình như vậy, thì mỗi một 30 phút thì sẽ khoảng tầm 20 câu hoặc là 15 câu, tức là trung bình từ 1 phút rưỡi cho đến 2 phút một câu. Và đúng là vấn đề mà cần concern nhất ở đây, đó là chuyện mà cái đề thi online thì có đảm bảo được cái sự khách quan cũng như là sự trung thực của các em hay không ấy, đấy để đánh giá được là sao đúng đắn nhất quá trình học tập. Thế nên là nếu tình hình mà cứ vẫn diễn ra là học online như thế này đến cuối thì chắc chắn chúng ta cũng vẫn phải tổ chức thi online thôi. Cô sẽ căn cứ theo lịch học của tụi em, còn nếu mà chúng ta sớm quay trở lại trường thì chúng ta sẽ học offline. Và cô cũng cô cũng đồng ý là cô sẽ gửi trước cái lecture note cho tụi em và các em có thể đọc trước này, vì có rất nhiều từ, ví dụ như hôm nay các em ngồi nghe ấy, có những bạn mà học tốt vật lý rồi thì và nhất các em học ICT hầu hết đều học tốt vật lý, thì nghe thì những từ như là phần optic assist, quang trục, cái thế nó cũng quen thuộc đúng không? Như trên hình chúng ta đang hiện ra đây này, hay là secondary wavelet, tức là các cái hàm sóng mới mà thứ cấp đấy, secondary là thứ cấp chẳng hạn. Đấy thì với các em có thể các em sẽ quen thuộc, nhưng có những bạn thì đúng là khi nhìn như vậy chúng ta cũng nên tra trước, hoặc là concave rõ ràng kính gương cầu lồi, gương cầu lõm nhờ, concave là gương cầu lõm, là convex gương cầu lồi, thì đấy là những cái thuật ngữ mới mà đúng là nếu cô mà gửi trước slide thì các em sẽ thuận tiện hơn để follow. Thế còn phần electricity and magnetism thấy Hưng có gửi trước slide không? Chắc là phần đấy thì Hưng cũng không gửi trước đúng không? Đấy, thế nhưng mà còn cái phần mà nếu mà trong tình huống chúng ta thi online hay offline thì các thầy cô cũng sẽ đều thông báo các em trước ít nhất là 1 tuần để các em có sự chuẩn bị. Và tốt nhất là đây từ ngay giờ dạy xong cô sẽ upload ngay cái lecture của ngày hôm nay và lecture buổi sau lên Moodle, và các em cũng có thể follow dần. Còn bài tập thì cô đã gửi list từ trước rồi, các em cứ làm bài tập dần đi. Và có cả cô khuyên các em nên đọc textbook nhé, dành thời gian đọc textbook, bởi textbook viết rất là chi tiết, rất là tuần tự, rất là câu chuyện kể sẽ rất là gọi là nó nhiều thông tin ấy, các em đọc các em sẽ dễ hiểu hơn. Những bạn nào mà các bạn nào mà trước đây chưa học kỹ vật lý chẳng hạn thì textbook lan man đấy là vì là mình cố gắng mà em đọc hết các chữ thì nó sẽ cảm thấy lan man thật, bởi vì họ viết đúng kiểu textbook là kỹ lưỡng đấy, nhưng mà mình phải có một cái kỹ năng, đó là kỹ năng đọc và lấy thông tin. Tức là đôi khi em nhìn thấy một cái thông tin rất dài, mình mà đọc từng chữ một ấy, mình hiểu hết từ từ thì nó rất là lâu. Nhưng rồi mình phải biết cái scan information để mình đọc, và sau đó thì mình sẽ thấy là cái câu chuyện họ viết nó rất là logic. Còn các em học các cái giờ lecture ở đây, kể cả là em tập từ tutor, thì các em sẽ các cái kiến thức nó sẽ được cô đọng lại nhanh gọn hơn. Các em đôi khi nghe các em sẽ cảm thấy là nó hơi bị hơi bị nhiều một lúc, rồi hơi mệt. Đó thì đấy là những cô rất là khuyên chính xác. Đúng rồi, các em đọc em đọc textbook thêm, nhưng mà còn cái phần optics thì trong cái phần slide cũng có khá nhiều chi tiết rồi, em cũng có thể follow được. Nhưng tuy nhiên là cô rất là khuyến khích tụi em nên đọc textbook. Với cả mình học đại học ấy thì mình cái hay mình gọi là càng lớn hơn, đó là mình khi mình đọc các cái cuốn sách kiểu như là textbook của đại học thì viết cũng sẽ rất là thú vị, em nên dành thời gian đọc. Thế nhá. Còn nghiện game thì ok. Nghiện game thì ok, ai cũng nghiện game thôi, thì enjoy thôi. Game và học, và cố gắng. Các em ở đây là rất chủ yếu là ở lớp ICT và bên toán các thứ, thì các em lưu ý là ICT tỷ lệ gọi là chưa qua môn cũng rất là nhiều, rồi tỷ lệ học bút khóa cũng nhiều đấy, nên là các em cố gắng cẩn thận. Thế nhá, cô bay cả lớp đã xong rồi, cô sẽ up lên Moodle các cái chương tiếp theo nha. Vậy nha, bye các em. Nếu có vấn đề gì thì cũng nhắn tin cho cô nhá, qua email. Bye cả lớp.
Bye professor.
Chào cô.
Dạ cô ạ.